So, hello and welcome to the last London Learning Lean of term. So next, Imperial's term starts next on the 4th of May, where we are possibly going to have Amelia giving the talk that she didn't give earlier this term on algebraic geometry on the tori in lean. But this week, it's Matej Penciak, whose name I hopefully not mangle too much, who's going to tell us about fast implementations of finite fields and elliptic curves in Lean 4. Over to you.
All right, thanks. So first I want to thank the organizers for giving me the opportunity to give this talk. I really love giving talks, and I feel like I learn a lot and I get a lot done preparing for talks. So this was a really great opportunity for me. So thanks again for the invitation. So as Kevin said, I'm going to be talking about fast with an asterisk implementations of finite fields and elliptic curves in Lean 4. And if you want to follow along, I've included a link to my slides over on GitHub. So if you get bored or you want to look ahead or whatever, you can look at the slides. Also on the repository, I included an annotated .bib file. So for any of the references that I have at the end of the slides, you can go over there and see what comments I have about the different references. So just as an outline for the talk, I'm gonna sort of just begin with a little bit of motivation for why we're even writing all of the stuff that we're doing at Lurk Lab related to elliptic curves and finite fields. So this will take us into a little bit about zero knowledge cryptography. And then finally, I'll get into the meat of the subject, which is some optimizations we've been working on to make finite field arithmetic and elliptic curve arithmetic a little bit faster. So the various optimizations are sort of included here, just listed out, and I'll go into each one of them a little bit more depth when we get to them. And then at the end, I want to end with like a brief demo just to show off like how easy it is to use all of the tools that we've been building. And then finally, some lessons learned and future outlooks for all of this work. So also, if you have any questions, stop me along the way. I like answering questions. I feel like talks make a lot more sense when people are interrupting and asking questions. So let's begin. So first, I should answer, who am I? So I'm a software engineer and aspiring cryptographer at Lurk Lab. So we were formerly named Yatima, I think, up until like 2 weeks ago or something like that. But we've gotten a new name, Lurk Lab. I'm very new to all of this. If you asked me what the most interesting things were exactly 1 year ago, I'd probably say something like moduli of vector bundles and abelian varieties and integrable systems and all these kinds of things. But I have left the ivory towers of academia, and now I'm working in the pits as a software engineer. And I learned so much in the last year, and pretty much all of the stuff that I'm going to say now is stuff I learned within the last year. So that's kind of a caveat to saying I'm probably wrong in a lot of places. And also, none of the stuff that I'm talking about today is original work, other than obviously the code that's been written. Though that also has been in conjunction with a lot of the other people at Lurk Labs. So Daniel, who's in the audience here, wrote a lot of this stuff along with me. And then there's other people who worked on the project as well. So Arthur, I think, is also in the call, and a few other people at Yatima or Lurk Lab. So what is Lurk Lab? So Lurk Lab, we're a company. We are building the Lurk programming language and an ecosystem of tools surrounding that language. So though it's not the focus of the talk, I want to focus on finite fields and elliptic curves. I think it's good to have a little bit of context for why we're building all of these things. So an example of some of the tools that we've been building is the Yatima compiler and content addresser, which takes Lean code and turns it into Lurk code, so that it can be run on sort of these zero knowledge environments. We've written a Lean type checker from scratch to be run as a Lurk program. And we obviously have been building a lot of this cryptography surrounding zero knowledge proofs so that we can start generating Lurk proofs of execution. So I've been saying a lot of these words like zero knowledge proofs, proofs of execution, etc. So what is Lurk? So Lurk is a Lisp-like language. If you look at the syntax for Lurk, you'll and if you know some Lisp, you'll feel very much at home. But what differentiates it from something like a common Lisp or a scheme is that it can generate zero knowledge proofs of execution. So some examples of what it can do is, like, if I have a Lurk program F, then I can run the computation F on some input U, and I can prove that I've run this computation correctly. Also, for example, I can, without revealing U, return a V, and I claim F. I know some U, which results, which when I apply it to, which when I apply F to it, I receive a V. Or like even more fancy things, like I can commit ahead of time to a program F, and then you provide me a bunch of inputs U, and I can run those executions and provide proofs that I've run those executions on all of these inputs U. And so there's a lot of interesting applications for these, the ability to do these kinds of things. But again, it's not sort of the focus of the talk. So I'll sort of leave those to maybe questions at the end if people are curious. But it is maybe worthwhile to say some words about what are zero knowledge proofs. So a modern perspective on zero knowledge proofs is that they're kind of built up out of two different systems: an interactive proof scheme, which is a interactive protocol between a person called a prover and a person called a verifier, where the prover is trying to convince the verifier of a certain fact, and they go back and forth trading messages, and eventually at the end of the protocol, the verifier, if the prover is being honest, should be convinced of the fact that the prover is trying to prove to them. And these interactive proof schemes should satisfy certain properties like soundness, completeness, zero knowledge, etc. And I'll get into a little bit of that later. And then the second aspect to zero knowledge proof schemes are so-called commitment schemes. An interactive proof scheme is a protocol, as I was saying, between party P, called a prover, and a verifier, where the verifier is trying to verify a fact that the prover is giving to them, where they're not necessarily supposed to be trustworthy. The prover is not necessarily supposed to be trustworthy. And a commitment scheme is another interactive protocol where one party is trying to commit to some data, so say a vector or a polynomial, and they want to commit to this data without revealing its value so that it can be opened later. So for example, if you want to imagine some application of this in something like an auction, where you want to commit to a certain bid, but you don't want the auctioneer or the other bidders to know what that bid is until eventually all of the commitments are opened at the very end. And if you combine sort of in some magical way these interactive proof schemes and these commitment schemes, you can get something called a zero knowledge proof scheme. And I won't say, again, I won't go into detail about this, but I'll give an example of an interactive proof scheme in a bit. Actually, I'll give it now. So we have two parties, P and V. So, in cryptography, usually you have an Alice and a Bob, but for these kinds of things, usually I think it's like Peggy and Victor or something like that. So Peggy and Victor, the prover and the verifier, they have two graphs, G1 and G2. And the prover wants to prove to V that they know an isomorphism of G1 to G2 without revealing the isomorphism. So this is going to be an interactive protocol between the prover and the verifier, where the prover is going to prove that they have knowledge of an isomorphism, but reveal nothing about that isomorphism to the verifier. And the proof scheme kind of goes in a number of steps. So the first step is that the prover chooses a random permutation of the first graph G1 and sends the permuted graph H to the verifier. The verifier then chooses... You
wanted questions, right?
Sorry?
You said you were happy with questions.
Yes, absolutely, yeah.
I'm already lost. What's a permutation of a graph?
It's just an isomorphism. Just permute the vertices. But make sure, obviously, that all the edges are still connected the same way.
Maybe my question then is, what's a graph in your... I don't understand what you mean by a graph.
Oh, edges and vertices, right?
Right, but given in what way?
You can...
I just didn't want to be lost at the very beginning of the talk. Sorry.
Yeah. So I mean, if you want to think about it as being encoded in a computer, you could do it in terms of like an adjacency list where you have, or an adjacency, or I guess, yeah, you maybe encode them as an adjacency matrix.
Okay, so
yeah,
right, so the graph is an adjacency matrix full of zeros and ones, and now what's a random permutation of that graph?
So it would be a like you would take your adjacency matrix and conjugate it by a permutation matrix.
Right.
And that would represent the same graph, like if you sort of drew it.
Okay.
Yeah.
So P and V both know this adjacency matrix.
Yeah, so they both know two adjacency matrices, both for G1 and G2. Yeah.
Got it. Okay, right. I'll now shut up. Thank you.
Yeah, no problem. Yeah. Yes. Ask away if anyone else is confused about this. So in the first step, the prover chooses a random permutation of G1 and sends that permuted matrix, or that permuted graph to the verifier. And the verifier then chooses a random number, 1 or 2, and sends that choice to the prover. And now the prover will respond with an isomorphism from phi1 or phi I from Gi to H. And so if the prover really did know that G1 and G2 were isomorphic, the prover should have no issue responding with this phi I. So for example, if in step 2 the verifier chose I equal to 1, then what the verifier or what the prover will do is the prover just sends what would they send? They would just send sigma, right? So sigma is kept secret from the verifier, or maybe not necessarily kept secret, but is not something that the verifier should be able to compute. Whereas if the verifier chose I2, then what the prover would send they would choose like sigma composed with like phi inverse or something like that, so that you go from G2 to H. No, I think sorry, I think it's sigma inverse or something like that. I don't know. It's not super important. And then, okay, so then in step 4, once the verifier has received this isomorphism, they just check, does phi I of Gi actually equal H? And if it does, then they'll be a little bit convinced, and you could repeat this protocol a number of times until the verifier is sufficiently convinced. And so why should the verifier be convinced at this point, right? So what if, like why should, if the verifier is always going to pick, say, 2, then the prover could lie to the verifier and say, oh, hey, I'm sending a permutation of graph G1, I promise, but actually be sending over a permutation of graph G2. And if they didn't actually know an isomorphism between G1 and G2, then that would be still a sufficiently valid proof, because they would be able to supply an isomorphism from G2 to this random permutation H. But the fact that in step 2, the verifier is choosing a random number between 1 and 2 means that the prover is kind of always on his toes. They're not totally sure, okay, well, if the verifier chooses 1 and I've chosen to send graph G1 in step 1, or if the verifier chooses 2 and I've chosen to send graph 1 in step 1, then I'm going to have an issue supplying this isomorphism from Gi to H if I don't actually know the isomorphism between G1 and G2. So there's kind of like a 50-50 chance at step 2 that the verifier has actually chosen the same graph that the prover has sent a permutation over of. And if you repeat this protocol, say like n times, then the verifier should be convinced that the prover could sort of falsify this proof with probability approximately equal to 1/2 to the n. So this protocol, as I was saying, is a zero knowledge proof protocol. So it should satisfy certain properties. So it satisfies completeness, which is the fact that if the prover is being an honest prover, then they should be able to convince the verifier in every case, depending on the in every case of the randomness that the verifier has chosen. It's knowledge sound in the sense that if the prover doesn't actually know the isomorphism between G1 and G2, they should have a hard time convincing a verifier. See, the graph isomorphism problem is NP complete. It's thought of as like computationally complicated problem. So it should be difficult for a lying prover to supply a fake proof, given that if they don't actually already know the isomorphism ahead of time. And finally, it satisfies this property called zero knowledge, and this is a property that the verifier learns nothing about phi from the proof that the prover sends over. So in the two cases, the prover either sends over this permutation sigma or this permutation sigma composed with phi inverse. So there's no real data leaked about the isomorphism phi, because the sigma is thought of as being a hidden sort of hiding parameter that the verifier, that the prover has calculated himself.
But you can work it out from phi 1 and phi 2, right?
Yeah, so that's why when you repeat this process, what you want to do is you want to go to the very beginning where the prover chooses a different random permutation, so that no data about the permutation phi is leaked.
Oh, we repeat from step 1.
Yeah. Oh, yeah. Sorry, I should say that. Repeat from step 1. Yeah.
Got it.
Yeah. Now, things that this protocol doesn't satisfy is it's interactive. So this protocol is not non-interactive, and it's not succinct. So the data that the verifier is sending over to that the prover is sending over to the verifier, if they're thinking about this as, if you're thinking about this as something like adjacency matrices, and these graphs as being very large graphs, you're sending like a very big blob of data over as the prover. And furthermore, if you're sending over isomorphisms in step 3, you're sending over an even bigger large blob of data, right? So this protocol is neither non-interactive or succinct. But via the magic of cryptography, we can generate zero knowledge arguments in this form, which are both succinct and non-interactive. And these things are called ZK snarks or zero knowledge snarks. And the goal of all of the cryptography that we're writing in Lean is to be able to sort of write these ZK snarks in Lean. So now a few comments about cryptography. So it doesn't really help to encode our computational problems in terms of graph isomorphism. It's really hard to go from, say, calculating the Fibonacci sequence calculating the balance of someone's bank account into some problem about graph isomorphism. So what we really do is we encode our computations in so-called arithmetic circuits. So what these things are is not super important, but the basic idea is that they're measured but they're basically these circuits where the computations are done on the level of finite fields. And so in order to have a certain level of security, you want to prevent that the prover, you want to prevent a dishonest prover from creating fraudulent proof. And a good estimate is about 128 bits of security. So that's kind of like the gold standard now for security in like internet protocols and these zero knowledge protocols. And so just a couple examples. So for example, the fastest known factorization discrete logarithm algorithm is based off the general number field sieve method, and it has a runtime of this form. And so to achieve about 128 bits of security, you need to use prime fields of size 2 to the 248. To 2048, right? So very large prime fields. Now, on the other hand, if you just take some generic elliptic curve E with a cyclic subgroup of points of size n, then as long as this curve is really sort of generic in a certain sense, it doesn't have sort of weird properties, then the best known attack on the discrete logarithm problem on the elliptic curve runs in time approximately square root of n. So in order to achieve 128 bits of security, now we actually only need to work over fields of size 2 to the 256, which is a great improvement. So you'll see giant primes and giant fields appearing in the context of RSA, but if you're working with elliptic curve security, you can work in much smaller fields. Daniel, yeah?
So I have a ridiculous question. So why publicly now known?
Oh.
You mean there are some people that know some better discrete logarithm algorithms without revealing them in
Yeah, I
terms
mean,
of this
I don't want to
presentation.
speculate, but I imagine that there's probably some very smart cryptographers somewhere working for some very smart national security agencies somewhere that could probably do better than this. But
Fair enough.
that's
Fair enough.
just speculation on my part. But yeah, so there are situations where you don't get 128 bits of security. So for example, if your elliptic curve is defined over FP, and the number of points on your elliptic curve is actually equal to P, there's a very simple algorithm that can break the discrete log on such an elliptic curve. And there's other cases as well. So for example, if your elliptic curve is defined over a finite field, which is has small characteristic but has a very large degree, then there's some things that you can do. Or for example, if your cyclic subgroup has large cofactor in your elliptic curve, there's some attacks. But just for generic elliptic curves, the best known algorithm is the Pollard-Rowe method, and has complexity O of square root of n. And so our goal is, right, to find elliptic curves with about 200 or 2000, or sorry, 2 to the 256 points. And Haas's bound for the number of points on elliptic curves basically makes it sort of easy to find elliptic curves with enough points. We just have to define some elliptic curve over a field which is large enough. So if P is about 2 to the 256, then the number of points on elliptic curve defined over P or over FP will be about 2 to the 256. But there's more engineering that can be done in order to find elliptic curves with more desirable properties. And we'll see some examples of elliptic curves later with some really desirable properties that make computing on those elliptic curves very, very fast. So just a comment about, so now, the setting has been set, right? Now we know that we're going to be working over fields of about size 2 to 256. So how do we actually represent these things? So just a comment, most computers don't know about numbers larger than, say, 2 to the 264 minus, or 2 to the 64 minus 1, basically Lean's data type UIT 64s. So what's done instead is that Lean 4 represents these NAT and these int type types, which are multi-precision data types, in terms of some external C or C++ libraries. And so if you actually look at the definition of NatAdd in Lean, you'll see that they're all, or NatAdd, NatSub, NatSuck, etc. They all have, a pure Lean implementation, but really in the runtime, when you tell Lean to evaluate some expression, it's going to be running some C program under the hood. And so what is that C program? I didn't include it in anywhere, but it's essentially, yeah, I mean, it's not super important, but what it'll do is it'll sort of unbox the numbers A and B, and then evaluate some big number precision arithmetic in C. So the multi-precision arithmetic libraries that Lean is based off of on Linux-based systems is the new multi-precision library, GMP. Mac and Windows get some homebrewed version, which is part of the Lean 4C runtime code, which is essentially equivalent. And the way that they represent these natural numbers is as arrays of UINT 64s. And if we want to, say, represent a number of size 2 to the 256, we essentially need 4 limbs of UINT 64s. And given that you're representing a number as UINT 64s, there's just the standard ways that how to multiply numbers in base 2 to the 264. You can use school book multiplication, which is where you do carry and multiply each thing, and then etc. But that has runtime O of n squared. There's a optimization, which is the Karatsuba multiplication algorithm, which has runtime of approximately O of n to the 1.58. And then what GMP uses is some variant of Strassen's fast Fourier transform algorithm, which has a much faster runtime, n log n. And so GMP is like super, super fast. And so the first foray into making things quick in Lean was we tried to write our own fixed precision arithmetic library in Lean based off of Lean's byte arrays. Lean's byte arrays are just basically in the C runtime, just basically like strings of zeros and ones. So it should be some and essentially all of the methods associated with byte arrays are externed out to C libraries. So in principle, it should be very, very fast to run these kinds of libraries based off of byte arrays. But it turns out they were about 100 times slower than just the native NAT arithmetic. So we quickly dropped that plan. Let me just make a comment about benchmarkings. So here I'm saying that we did some benchmarking. We saw that it was 100 times slower. So how did we really learn that it was 100 times slower? So just a quick comment about benchmarking and testing. So because we're implementing algorithms and not really proving anything about those algorithms, it's important to have a testing and benchmarking framework so that we have an idea of whether we're on the right track, whether we're actually calculating the right values, and whether we're doing them efficiently. And so for testing, one of the first things that we built at Yatima was a testing framework, which we call LSpec, which ended up being, a huge savior for a lot of things that we're doing. And so it's very fast and it's very expressive and it's very easy to use. And so, for example, you can write things out like check whether AddCom is true for nets, and it'll sort of try a bunch of different natural numbers and test if it works. Or, for example, you can check some statement that's not true, and it'll test random numbers and eventually find some counterexample if the fact isn't true. And so as long as you do a little bit of work ahead of time so that you can generate these random examples of natural numbers or random examples of vectors or random examples of matrices or whatever, then you should be able to sort of plug them into these LSpec tests like this and be able to run tests very quickly. On benchmarking, similarly, we have like a very simple benchmarking framework. Here is an example of using this benchmarking framework to compare a native natural number exponentiation with a fast exponentiation that's defined in a different library. And you just basically define a benchmark, which would be comparing the two functions f1 and f2, give it the set of inputs, define the main function, and compile it. And then in the compiled version of the function, you run it with a sort of a number of iterations that you want. You log out to a file or either log out to standard output, and you can get sort of results like this. So really quickly compare the relative performance of different algorithms. And so this benchmarking tool is super, super important so that we can test whether we're on the right track for these efficiencies that we're trying to implement. Okay, but now back to fields. And so now that we have it, now that we have our setting that we know what we're trying to do, we're trying to implement finite field arithmetic. We started building out the type classes that are associated with it. And so a lot of these will look familiar, ring and field, for example. So the ring type class has all of the arithmetic that we need. Field is that together with inversion. But then we included some more type classes which have special properties which are useful in different settings. And so as a couple examples, and then I should say, these are not, there are no prop valued fields in these type classes. And so we're not saying that the addition that you define on a ring is commutative or that the multiplication distributes over addition or anything. That's kind of up to the implementer to make sure that they're actually providing lawful instances of these things. They're not formalized, but they're not formalized yet. So I'll get back to that at the very end.
So why do you mention NewField? Because we have recently renamed NewField to PrimeField and got rid of PrimeField a couple of days ago.
I'll explain at our meeting later today.
Okay.
Okay. So this is kind of the hierarchy for how different things extend what. The ring and field provide the basic arithmetic properties about rings and fields. Galois field is here so that we can start talking and doing computations with field extensions. Prime field is so that we have some additional optimizations that are available for fields that are of prime order. And then finally, NewField is here so that we have some additional optimizations related to Montgomery form, which I'll say some words about in a few minutes. So here are some examples of the type classes that we've implemented. So ring is kind of exactly what you would expect. It has add, mul, sub, powers, Boolean equality, etc., and also two numbers two distinguished elements 0 and 1. Prime field is similar to field, or rather it extends field, and it has a bunch of additional properties. And so here you'll see that it allows us to take square roots, which we, for instances, have implemented using Tonelli-Schenck algorithm. It has some pre-computed values, which I'll say some words about in a bit. It has some ways of representing and coming from natural numbers. And then finally has some batched arithmetic operations. And so, so the next step, what I'll talk about is what these pre-computed values actually mean. And then I'll say some words about what this batched arithmetic optimizations allow us to do. So exponentiation, very commonly performed operation on finite fields. The naive implementation of defining a to the n as a times a to the n minus 1 is obviously too slow when you're going to be taking things to like 2 to the 256 type powers. So what you replace that with instead, in a very naive sense, is the square and multiply method. And so you essentially take n, write it out in its binary expansion, and you just either square it or multiply it with a different power until eventually you build up a to the n the way that you would want. But this square and multiply method requires about 3/2 log n operations, which is, it's a lot faster than O of n, but it's unfortunately a little bit slow. Or it's not a little bit slow. It has the potential to be a little bit slower than the optimization I'm about to say. And I should say that I should give you a warning. This warning is a common warning for a lot of these cryptographic algorithms, that this double and add method or the square and multiply method are susceptible to timing side channel attacks. So if you're curious about what those are, ask me at the end and I can explain a little bit about that. So the idea though is that when you're going to be taking exponentiations of things that you know you're going to be doing very commonly, like p or p over 2, or sorry, p minus 1 over 2, so for the Frobenius or for calculating Legendre symbols, then we compute these so-called minimal addition chains, which are just lists of numbers n1 up to nr, where the last number is the n that we're interested in, so that ni is a sum of nk and nl, where k and l are less than I. And so if you can write an addition chain for n in this way and find one that's minimal in this way, then you can build up an exponential of a to the n in terms of field operations, which are exactly of length the addition chain that you've generated. So as an example, if we want to calculate the Frobenius modulo this very large prime here, just using the simple square and multiply method, it'll take 381 field operations. But with a pre-computed minimal addition chain, we can reduce that down to just 337 field ops. And so this difference of what, like 44 field ops doesn't seem like that much. But if, say, for example, you're generating 60,000 or 600,000 different elliptic curve points, and for each one of those elliptic curve points, you're going to have to calculate either a Legendre symbol or a Frobenius or something like that, just the amount of time saved by reducing the amount of field operations that you're doing ends up actually adding up over a significant, up to a significant amount.
As far as I understand, it could make more sense if we compare two performances in terms of percentages, not just to numbers. So I mean the second variant has I think so it has
It's like almost 10% faster.
Yeah. Oh yes. Oh yes.
A little bit more than
I was trying to compute the percentage,
Yeah,
which is tricky for mathematicians sometimes.
yeah. Yeah, it's a little bit less than 10%, but it is a nice little boost in performance.
Oh, so 10%. So it sounds like a very considerable proportion, as far as I understand.
Yeah, it helps. I mean,
Okay.
it's not like a 10x improvement or something like that, but it helps.
Okay.
So other implementations that we've included is, for example, this batched inversion implementation. So exponentiation is costly, so is inversion in a field. So if we're doing inversion in Z mod PZ, then we're using about log P operations, using the extended Euclidean algorithm to find the inverse. So the idea behind batched inversion is we can invert a bunch of field elements all at once, using only a single field inversion. And so the idea is what you do is you calculate a lot of these intermediate products n sub j until eventually you get nr, which is the product of all of them, invert that last element, and then you recover each one of the ni inverses by multiplying by cached results. And so I've done a small example here, but in the interest of time, I'm just going to skip over the example. But the upshot is here, what you can see is that we've replaced our field inversions with just a single field inversion at the cost of about O of 3R field multiplications. So we're saving some time there. And if you have this method available to you, then you can do some tricky things with your algorithms to take advantage of this method. And then finally, Montgomery form, I'll skip over this relatively quickly, but the idea about what Montgomery form is trying to solve is that you want to calculate A times B mod P, but you don't want to, if say, for example, you have a lot of multiplications that you're going to be doing in a row. So for example, if you're taking the exponential of A, then you don't want to have to calculate A times A mod P, and then A squared times A mod P, and then A cubed times A mod P, where you're reducing mod P at every step. And the sort of solution to this, or the intuition behind the solution, is that you replace reduction modulo P with reduction modulo R for some other R. And so in practice, what you do is you choose some R that's bigger than P, coprime, where division and reduction modulo R is efficient. And in practice, really what you want to do is you want to choose R to be some power of 2 that's greater than P. In principle, right, on a computer where everything is represented in its binary form down like on the level of bits, reduction modulo P, or reduction modulo some power of 2 is very simple. You just truncate your bit representation at a certain point. And division modulo R should also be very simple. It's just a bit shift left, or a bit shift, it's a bit shift left, right? And so reduction modulo R and reduction modulo division modulo R should be very, very fast compared to modulo P when P is not a power of 2. And so the idea in Montgomery's form for numbers is that you replace a number with its Montgomery form, which is sort of this wrapped form here, where you take n and you replace it with n times R mod P. And Montgomery reduction is an efficient way of calculating n R inverse. And so that allows you to take addition, which is just usual addition modulo P, but then multiplication together with this Montgomery reduction algorithm allows you to calculate n times m in a very quick way, without having to ever take things mod P. And so we actually implemented this in Lean, and we actually implemented a macro rule that expands a declaration that looks like this into a type test field, which has all of these pre-computations done of addition chains, has all of these batched inversions and batched exponentiation algorithms already at your fingertips. And it also implements things with Montgomery reduction so that you can hopefully do things a little bit faster. And so the asterisk in fast is starting to rear its head here, where it's actually not advised that you use this implementation of fields yet, until there's a little bit more work done in terms of bringing in GMP into Lean. So the reason is, if you're taking reduction modulo R or reduction modulo 2 to the R in Lean, there is no performance benefit over taking reduction modulo P. And that's because there is no special reduction modulo some power of 2 in Lean yet, because it all depends on this additional GMP method that hasn't been exposed in the runtime for Lean's NATs. So there's a little bit of work that needs to be done in order for this implementation to be as fast as NATs. But for now, it's still usable. It's not that much slower, but it doesn't provide the performance benefits that you would hope from Montgomery reduction. Okay, so got to start breezing through these last few slides, but now we're going to start talking about curves. So say you have fast field implementations already, and now we want to start doing operations on curves. And so the immediate goals that we had for elliptic curves at Yatima is that we want to start working with curves over fields of large characteristic. So we don't have to worry about characteristic 2 and characteristic 3. So there's no issues in just representing a curve in terms of its Weierstrass form. On the other hand, arithmetic on elliptic curves is a little bit more complicated. So we have this curve group class, and we do some work in order to separate out the curve's arithmetic from the curve itself. And the reason for this is because you want to be able to allow for different coordinate systems on your curve to do efficient arithmetic operations depending on the context. So for example, projective coordinates allow you to do addition and division, or sorry, addition and doubling without having any field inversions. Whereas affine coordinates have one less field element that you have to store on disk, so it's more compact on disk. And then finally, like there's even more exotic coordinate systems where doubling is more efficient, where at the cost of making addition of 2 points slower. And these different more exotic coordinate systems may have benefits in different contexts as well. So we want to separate out the curve from its arithmetic by separating it out into these 2 separate classes. So really just to show off the fact that people have thought a lot about what the different kinds of coordinate systems have in terms of their benefits. This is a chart taken from this book, the Handbook of Elliptic and Hyperelliptic Curve Cryptography, which really spells out the cost of all of the different operations that you can hope for in the different coordinate systems. So P here is projective coordinates, the affine ones are down here, and these G's or these J's are either Jacobian coordinates, Chudnovsky Jacobian coordinates, or modified Jacobian coordinates, etc. And so there's even more coordinate systems on top of these, like Edwards forms and Montgomery forms, and so much more. And then furthermore, even once you choose a coordinate system, you have the naive algorithm that you see in a book, and then the actual algorithm that's implemented in Lean. And so here's an example of how we've implemented, I think this is addition in Lean. And the reason why we're doing it this way is because you really want to ensure that the number, if you just write that formula out, you don't know how Lean's going to evaluate that arithmetic formula. So you really want to ensure that the arithmetic formula is done in such a way so that you're minimizing the number of field operations in order to compute, say, addition of points or doubling of points. And so this is just a screenshot from the elliptic curves library that we have, showing off, the crazy kind of code you have to write in order to get like efficient addition and efficient doubling for projective coordinates. So once you've chosen your coordinate system, given the cost benefit analysis from before, you want to actually start doing things with it. So say scalar multiplication, which is the problem of finding n times p for n a natural number and p a point on your curve. And you can even speed these things up a little bit depending on the curve you're working over. And so in the special case where your curve has prime order q and an efficiently computable endomorphism phi, then phi of a point, well, it has prime order, it has to be another point on the curve. So it's going to be some multiple of that original point p. And so that number we'll just fix as lambda. And the idea is that once you know an efficient computable endomorphism, you can reduce the scalar multiplication for n times p into two separate scalar multiplications, n1 times p and n2 times p, where n1 and n2 are of size square root of n. And the way one does this is you find this, you pre-compute this lambda, and you use lattice reduction methods to write n as n1 plus lambda n2, and then n times p ends up being just simply n1 times p plus n2 times the efficiently computed endomorphism phi of p. So notice here that we actually aren't multiplying lambda times p. We're just multiplying n2 times phi of p, where phi is this efficiently computed endomorphism. And so an example of a curve that has this property is if your curve is of the form y squared equals x cubed plus b, then if you take zeta, a primitive cube root of unity, then phi, which takes your coordinates and just multiplies the x coordinate by zeta x, this is very fast computed endomorphism. It's just a single field operation, and it can reduce your the cost of your scalar multiplications by half. And we've implemented this, and for particular curves, for particular curves that we've implemented this for, we see about like a 50% improvement in scalar multiplication efficiency. And then just a comment about this optimization was actually subject to a patent which only expired in 2020. So you're safe to use it now, but before then you would have to maybe provide some royalties to the people who own the patent. And this is called the GLV optimization for the three authors who patented it and wrote the paper. So now a couple magical curves that have this optimization. So the magical curves are the so-called Pallas and Vesta curves. So the curve equations themselves are just y squared equals x cubed plus 5, and they're defined over the points, the fields fp and fq, where p and q are these two very large primes. You see that they're very close to each other, but they start differing sort of at this point right here. The nice properties that these, so Pallas and Vesta have been concatenated into pasta. The nice properties these pasta curves have is that the number of points on one is equal to the base field on the other. So they create a so-called cycle of elliptic curves. And finding cycles of elliptic curves is really important for recursive zero-knowledge proofs in zero-knowledge cryptography, but also they're very important for but they're also very hard to find. And so it's kind of a magical property that these two curves have this weird cycle property. And as we saw before, they have an efficiently computable endomorphism, and they have some other nice properties like a large two-adicity, which helps when you're going to be doing some fast Fourier transforms in some protocols. The primes are of the form 2 to 255, plus some small quantity, which helps reduction modulo p to be very efficient. And then this last property about having low degree isogenies allows you to generate random points efficiently. So I may skip over multiscalar multiplication here. So there's a nice implementation of Pippinger's algorithm for multiscalar multiplication that we've implemented. The reason why multiscalar multiplication efficiency is important is because about 80% of the time used in generating some zero-knowledge proofs is in the multiscalar multiplication case. And you're going to be doing multiscalar multiplication where the number of points that you're calculating the exponents of is about 2 to the 28 or up to 2 to the 28. So you're doing some really heavy computations here, and it's important that you make this step as efficient as possible. Where multiscalar multiplication in this case is the problem of calculating the sum here, sum of ni gi for points gi and numbers ni in your elliptic curve. So I think this is a 50-minute seminar, right? So I should probably just go to the conclusions real quick. Is that right?
Yeah, I think you can continue if you like for another 5 minutes or so.
Okay.
Should be fine.
Okay, let's see. So there's Pippinger's algorithm, and let me just end with a small demo. So let me stop sharing this screen and then start sharing my VS Code screen. Okay, so can people see my VS Code setup here? Is it small enough or large enough for people to see? Thumbs up.
That's fine.
Okay. Yeah, so let me just show you a quick demo of everything. So we can do, let's define our field. So this is a field which is going to be characteristic 2011, and let's we need to have a generator, say generator 7. So I checked 7 is a multiplicative generator for 2000 for F mod or Z mod 2011. We can define, or we can check things like we can calculate the root of unity in this demo field. We have field dot we have the Legendre. So in order to calculate Legendre symbol for an element in our field, we have this sort of ingredient here, which is the minimal addition chain that's necessary in order to calculate an exponent of p-1/2, etc. So we have a bunch of these nice properties about nice things that we've generated using demo field, and you can do demo field arithmetic. But let's do something even cooler. So let's define a demo curve, which will be a curve defined over demo field with coefficients, say A is 0 and B is 5. So here we've defined an elliptic curve, which is like this. We can define the demo group to be projective points over the demo curve. And we can even check things like, let's get all the points for the elliptic curve. And so demo curve.points returns all of the points on the elliptic curve. So say, for example, if I take P to be, let's say, how many points are there in this elliptic curve? This is size 1983. So let's take, like, say, the 391st point, and let's take the say 400th point, and we can evaluate like P plus Q. We can evaluate like 39 times P plus 41 times Q, and we can do very quick arithmetic operations like this. And yeah, so that's just kind of like a quick demo of all of the various optimizations and implementations that we have for this. And let me just again end with a screen which I'll let you guys read while I possibly answer questions about lessons learned and outlooks for all of this kind of stuff going forward. But yeah, so thanks for listening. Sorry I went a little bit over, but yeah, thanks for your attention.